Hello all, my name is Kanan Panchal and today we shall discuss surface and interfacial tension. In this video, we shall go through the different methods for measuring surface and interfacial tensions such as the capillary rise method and the Juno ring method. We shall also study the concept of spreading coefficient and the different interfacial phenomena. Now these are the different methods of determining surface and interfacial tension. You can select a particular method based on whether you want to determine surface tension or interfacial tension. What is the accuracy and convenience of the method you are looking for? Also, what is the sample size available with you all? However, capillary rise and Duno ring are the more commonly used methods. Now, drop rate, pendant drop, sessile drop, and oscillating drop together are known as drop methods. So, have you ever observed how your cold drink rises up the straw you used to drink? That is nothing but because of the capillary rise phenomena. The straw here acts as a capillary. So, this happens because the force of adhesion between the liquid and the capillary wall is greater than the cohesive force between the liquid molecules. Now, because of this greater adhesion, the liquid is able to wet the walls of the capillary and spread over it, thus rising up in the tube. Now, this method only tells us about the surface tension. It does not deal with the interfacial tension between the wall of the capillary and the liquid inside. So to understand capillary rise method, let us assume a capillary dipped inside the liquid. Now it will rise up to a certain point. Beyond it, it won't rise. So we'll wait till it attains that height, and that is considered as H. So the liquid up till this point, the height up till this point is given as H. Now, because of surface tension, the liquid is going to rise. But due to the weight of the liquid, this upward movement is going to be balanced by the downward force. So this upward component is given by this equation, A equals to y cos theta, where theta is nothing but the contact angle. This is the contact angle. A contact angle is nothing but the angle formed by the tangent to the surface of the liquid and the surface of the solid container. So when you further solve this, we get 2 pi r gamma cos theta, where 2 pi r is the circumference of the meniscus, gamma is the surface tension, and cos theta is the contact angle. Now the downward component is given by pi r square h, rho minus rho naught g plus w, where pi r square h makes up the volume of the liquid, rho is the density of the liquid, rho naught is the density of the atmospheric air present, which we neglect and consider it to be 0. G is the acceleration due to gravity, which will remain constant. And W is accounted for the weight of the liquid, which is right above the meniscus, which is this part right here. But for experimental purpose, we further neglect it and consider that to be 0. So when we further equate the upward component and the downward component, we get this equation. And on further solving, we get the final surface tension as half R H rho G, where R is the radius of the capillary tube, H is the length of the column of liquid, rho is the density of the liquid being tested, and G is the acceleration due to gravity. Capillary rise is also given due to the pressure difference across the curved meniscus. Now this is based on the principle that the pressure on the concave side of the liquid is greater than on the convex side of the meniscus. So based on this, you get an equation of 2 gamma by R equals to rho gh. And on further solving it in terms of gamma, you get gamma equals to half RH rho g, which is similar to that obtained by the previous method. Now let's move on to the Juno ring method. This is the Juno ring tensiometer, where this is the main apparatus. This is the ring. This is the liquid of which the surface tension is going to be measured. This is an appendage which connects the apparatus and the instrument which determines the force. Now this method helps us determine both the surface and interfacial tension. So here in the animation you can see how the ring is first immersed in the liquid and there is a point at which it detaches itself from the surface of the liquid. This is based on the principle that the force necessary to detach the ring from the surface of the liquid is proportional to the surface or the interfacial tension. So based on that, the formula for surface tension or the interfacial tension is given by this equation, where the dial reading is nothing but the force in dynes, which is nothing but mass into the acceleration due to gravity upon 2 into the ring circumference and the correction factor beta. Since the equation doesn't take into account the radius of the ring, the radius of the wire used to make the ring, or the volume of liquid raised out, we use the correction factor beta. And in case if beta is not used, errors as large as 25% may occur, which is huge. Therefore, two pairs of scientists have worked on determining the value of beta. Zidema and Waters have given an equation where this is A actually, where A, B and C are constants. Capital R is the radius of the wire. M is the mass of the liquid raised out of the surface. G is acceleration due to gravity. And rho 1 and rho 2 are the densities of the two liquids making the interface or density of liquid and air making up the surface. Whereas Harkins and Jordan have given standardized value of beta based on the radius of the ring. Small r is the radius of the wire used to make the ring and V is the volume of the liquid raised out. So when you know certain value for r cube V and r by r, you thus obtain the value of beta. Now let's understand spreading coefficient. Let us take an example of water and oil put up on the water. As soon as you put this oil or fat and form a duplex film. Now this is called a duplex film as one of its surface is exposed to water and one of its surface is exposed to the atmospheric air. However, both of these surfaces do not interact with each other and do not have any effect on each other. Now this spreading occurs because the force of adhesion between the oil molecules and the water molecules is greater than the force of cohesion amongst the oil molecules. So to first understand spreading coefficient, let us look at work of adhesion and work of cohesion. Work of adhesion is nothing but the energy required to break the attraction between the unlike molecules, that is liquid and the solid substrate. As per the previous example, it can be the water and the oil. Work of cohesion is the energy required to separate the molecules of the spreading liquid, or in the previous example, it can be the spreading oil, so that it can flow over the sublayer. Therefore, the work of cohesion is given by 2 gamma L and work of adhesion is given by gamma L plus gamma S minus gamma Ls. Here, since we are dealing with the same like molecules, there is no interface. Hence, the term which is used here is not used here. Now, spreading coefficient is nothing but work of adhesion minus work of cohesion, which is further written as this. Therefore, spreading coefficient is equal to gamma S minus gamma L plus gamma Ls, where gamma S is the surface tension of the sublayer liquid, here water. It can also be a solid substrate. Gamma L is the surface tension of the spreading liquid, and gamma Ls is the interfacial tension between these two liquids. Now, if this value, that is WA minus WC, is positive, then the oil will spread over the water surface. Spreading is also given in terms of surface free energy, where if the free energy of the old surface is greater than that of the new interfaces and surface formed, then spreading will take place. Now, if gamma S is greater than the summation of these two terms, spreading will occur. If gamma S is negative or lesser than the summation of these two terms, then instead of spreading, there will be formation of globules or lenses which will float above the liquid. Now at some point, the water and the spreading material above it may become saturated with each other. Now, when this mutual saturation takes place, the spreading coefficient S reduces, or it may also become negative. So, at that point, what happens is that the excess materials coalesce. They will coalesce into lens or certain globules and start floating above this liquid beneath. That is water. Now, this is a very good example of organic liquids spreading over water. Here are more examples of certain substances and their spreading coefficient at 20 degrees Celsius. Here we see ethyl alcohol and propionic acid having very good S values. That is probably because they are having good hydrophilicity. Benzene and hexane are having less S value as compared to them. Here you see ethylene dibromide and liquid petrolatum showing negative S values. Now this is because these substances are having higher hydrophobicity. This is all about spreading coefficient. Now there are two types of interfacial phenomena, adsorption and absorption. In absorption, you can see that the molecules are going all the way inside of the central molecule. That is due to the presence of pores on this central molecule. Example, absorption of water by the sponge. And in adsorption, they are just settling on the surface of the central molecule. Now, these green molecules are called as adsorbates, and the central black molecule on which it's settling is called as the adsorbent. Adsorption is further divided into two, positive and negative. When these adsorbates prefer to settle at the interface, that is, their concentration at the interface is higher than that in the bulk, it is called as positive adsorption. And when they do not prefer the interface, that is, their concentration in bulk is greater than that of the interface, it is called as negative adsorption. So in positive adsorption, the surface free energy and surface tension decreases. But in negative, these two phenomena increases. Adsorption's example can be adsorption of dirt particles by activated charcoal. So I hope you all understood these concepts. Thank you.